Okay, I guess I'm recording. Yeah, looks like it. All right, so let's talk about experimental motors and how not to kill yourself. Well, first things first, safety. I don't recommend to build your own motors, but if you decide to do that, well, if you want to do this legally, first of all, you need to get a permit from ATF. That's the Low Explosive Uses Permit. And some of the things to keep in mind when you build your own motors, of course, use common sense. Don't do stupid things. Don't expose your propellants to open fire when you don't want it. You need to know your mixture and all of the ingredients, and you need to know everything about it. That's why you need to read MSDS, Material Safety Data Sheets. They look like that. You'll commonly see this interesting symbol down there. It tells you about the most common hazards. And basically, you need to read the entire thing. You need to know what your materials could react with. You just need to be cautious about it. Start with small motors. Don't go big at first, and then slowly scale up as you get more experience. Keep your ingredients away from test area. It happened to me once that I was testing a small motor, but I forgot to take away an entire container with black powder. It was right next to it, and I was pretty lucky that it didn't ignite. That was stupid. Keep your fire extinguisher ready, just in case something goes wrong. A very important rule: cover your eyes and face, ideally with a face shield, not a face mask like this. Always ignite from distance using electrical igniters. Never do it like by hand. And always assume that your rocket will explode. It's gonna keep you safe as long as you know that you need to be, certain distance away from your motor, and so on. The final rule I haven't put up in here: if your igniter fails, wait 60 seconds at least before you approach your motor. I've seen some rockets that after igniter failure started running like after 10 seconds. It can happen, even though you think that is completely shut down. Okay, so we talk about these. Now let's talk about types of solid propellants. So the first thing you would use would be a pressed powder propellant, right? So an example could be black powder. The finer the powder is, the better the mixing and the higher specific impulse you can get. So keep that in mind, that generally the lower the mesh you have, the better it is. Now with powder propellants, they typically have little ISP. And imagine the main problem is, imagine you've got your rocket, okay? For example, this, can you see that? And you've got all that black powder inside it. You put it vertical, and it starts coming out from your nozzle. Well, that's pretty bad. You probably would prefer your propellant to be a solid piece, right? Something that doesn't move, something that's not going to come out when you're able to launch it. And that would be a composite propellant. So you could mix your oxidizer and fuel with some sort of binder, something that holds everything else together. And also the binder could be fuel. It could also burn, right? And another interesting property of composite propellant is that it should be elastic to prevent any cracks. The burn rate, we're going to talk about burn rate in a moment. It depends on the exposed surface area. So if your propellant suddenly cracks, you suddenly have more surface area. So suddenly your thrust goes sky high and you've got to explode pretty much. That's why you want it to be elastic, right? If you have some hard start, if you got like a lot of force working on your rocket, you want your propellant to be elastic. You don't want it to crack. Okay, some of the ingredients. Oxidizers, we're gonna talk about it in a moment. They are pretty much free. That we're gonna focus on. Fuel. There are a bunch of different types of fuel. Pretty much everything that has carbon in it can burn. So you definitely heard about sugar rockets, or also known as rocket candies. Charcoal is very popular fuel for solid rockets, solid motors, but it could also be metals. It could be aluminum powder, it could be magnesium powder, and it could be mixtures of everything I previously mentioned. There are also burn rate modifiers, which are also like fuels. They also burn, but the aim is to basically increase burn rate. So sulfur, it works very well with charcoal. It basically gives you a black powder. Or you could use iron oxide or copper oxide. They also increase the burn rate quite significantly. And then we have our binders. So a binder could be an epoxy, right? Not necessarily the same epoxy you use, for example, to hold your fins. Because this epoxy, you can see in here, this structural epoxy, right? So its aim is, it's very rigid. This epoxy is meant to hold something. But there are different kinds of epoxy that are very not viscous, right? They are liquids. They're not hard as this. And they could work for composite propellants pretty well. But the most common thing used in industry, it could be used by amateurs as well, is HTPP. It stands for hydroxyl terminated polybutadiene, something like that. There are several kinds of it. The first one that you can see in here are R45M. It's the cheapest one, but it's pretty viscous, so it might be quite difficult to mix it. A recommended one is R20LM, which is basically easier to mix. There are other stuff. There are plasticizers, stabilizers, and so on. I'm not going to talk about them this time. So let's focus on oxidizers. There are only three worth consideration. These are the only ones that are stable and give you reasonable specific impulse. Sorry, there's also fourth one. There's potassium perchlorate, but we're not going to mention it. So the most popular in industry is ammonium perchlorate. This gives you the highest ISP, but it's pretty nasty stuff. It's toxic due to chlorine. Pretty much everything that has Cl in it, I don't know if you can see my cursor, that's going to make it toxic, right? So ammonium perchlorate is cheap, but it's reactive. It can react, for example, with your clothes, and it could spontaneously ignite. That's pretty bad. Ammonium nitrate is much safer. It theoretically can detonate, but only if you have large amounts on it. By large amounts, I mean like entire bottle, right? And it's also very cheap, and it's much more widely available than ammonium perchlorate. Now, the stuff that I recommend is potassium nitrate. You can see that ISP is significantly lower, but potassium nitrate is the safest thing. It's used as fertilizer. You can buy it as stump remover. It's pretty cheap. It's not toxic, and there's no way it's going to react with anything that you can use. It won't burn your nose. That's important. The drawback of that is that it's slightly more difficult to ignite than the other two, but it's still not too difficult. Okay, so first choice for amateur rocket. What would you use? Which oxidizer? Which formulation? What about rocket candy? Sugar rocket? No. I know this one is the most popular. I know there are a bunch of YouTube videos on how to do that, but please, guys, do not do that. And the reason behind it is very simple. The melting point of sugar is 370 something Fahrenheit, and the auto ignition temperature is slightly higher. When you prepare a sugar motor, it's recommended, I mean, people recommend to caramelize it first, right? So you put sugar, you put your potassium nitrate on a saucepan or whatever, and you fry it in your kitchen. No, that's a stupid thing. Don't do that. If you bring it to 360 degrees Fahrenheit, the sugar starts to caramelize, and you'll get something like a composite propellant, right? It's going to be elastic and solid and stuff. Nice. But if you make a small mistake, if your temperature is slightly higher, then the thing is just going to ignite. And if you do that on a gas stove, it's certain to ignite. On electric stove, possibly you could do that, but you need to measure it all the time. You need to mix it all the time. You need to make sure that you've got no hot spots. Otherwise, the thing's gonna ignite, and that's bad. What I would recommend instead is just a classic black powder rocket motor. So use some potassium nitrate. You use charcoal and sulfur. Typically, you've got around 60 to 80% of potassium nitrate. Sulfur affects the burn rate. The more you have, the faster your propellant burns. In the most typical black powder, the one that just goes in guns, for example, the ratio is 75% of potassium nitrate, 15% of charcoal, and 10% of sulfur. The burn rate is too high for rocket motors, but we're going to use it for calculations just to give you an example. Okay, what our first motor would look like. You could make it out of PVC tube. Let's start small. Let's start with something small. So you could use 1/2 inch PVC tube. And all you need is, as you can see in the diagram, propellant in the middle, and you just cover, the ends with bentonite clay. Very cheap stuff. You can get it on Amazon. And then you just drill one end to have the nozzle. Don't worry about the shape of nozzle. Don't try to be, perfectionist. This is just your first motor. Just make it work, right? Don't worry about optimization, nothing like that. And then your igniter. How to make igniter? Bunch of videos on YouTube. Maybe I'll make my video as well. All you need is just a regular match, and you wrap it with nitron wire. Nitron wire is a resistive wire. If you apply current to it, it's going to burn. So this is a good igniter for a match, and then match definitely will ignite the black powder. Yes, you need some kind of a launching device. Maybe I'll send out a link to it later. There's one available on Amazon for $20. And it has these alligator clips. So you clip onto your nitron wire, and then from safe distance, from at least 5 meters, you press the button and the entire thing ignites. And it's really nice to watch. Here in that video, you've got detailed instructions. It's pretty straightforward. Not much I need to explain. And you can play with different propellant formulations. You can try more sulfur or less sulfur and see how it burns. Okay, now if you want to scale up, let's look into some equations. The actual equations are complicated, like ridiculously complicated. You may love it, you may hate it, but I'll try to keep it simple for you guys. Okay, first thing first. Rocket nozzles. I talked about them in previous video. Just to make it clear, we can use some subscripts in our equations. C stands for chamber. So for example, PC is chamber it's pressure in combustion chamber. T stands for throat. That is the smallest distance in the nozzle. And then E is the exit. Okay, the most important equation in solid propellants is the equation the depth per unit time per second, for example. And it depends on your propellant formulation, of course, and on your chamber pressure. Keep in mind, chamber pressure is the most important design parameter. It's going to affect everything. And you decide what it should be. You should assume a value based on what your casing allows, right? So, for example, if you go to a store or whatever, you check up what pressure PVC can withstand, and it's going to tell you, for example, 500 psi. Give it some safety margin. Assume that assume 400 psi, and that's going to be your assumption for PC for your calculations. Okay. If you go above the recommended, pressure for PVC, it's starting to explode. So keep it low. Okay, C and N. These are coefficients determined empirically. You should be able to find them online for your formulation. If you don't, there is a way to figure them out. You basically need to conduct a bunch of experiments. You need to measure your chamber pressure. You need to measure your burn rate. And if you do that for 10 motors, you'll get your coefficients. So it's pretty time consuming, right? But if you really want to do that, you can do that. Okay. Second equation, mass flow rate. Well, once you calculate your burn rate, if you multiply it by area, cross-sectional area, you've got volume burning per time, and then you multiply it by density, then you've got mass burned per unit time. In other words, mass flow rate. And then the final equation is thrust. Thrust from fluid mechanics, you'll see it commonly if you study fluid mechanics, is mass flow rate times velocity, in this case, exhaust velocity. And it also can be written in terms of specific impulse. So if you know your specific impulse for your propellant formulation, and you know your chamber pressure, you know geometry of your motor, you've got thrust. Simple as that, right? These are just simplified equations. I assume that everything is constant, which is not true. In rockets, everything changes all the time, right? But if we do simple end burning motors, things are more or less constant. Okay. Sorry, Ethan. If you have any questions, feel free to interrupt me. I don't know if anyone else is connected as well. If you have questions, feel free, guys, to interrupt me and ask. Okay, let's do our example. So we make an assumption for our combustion chamber. We check up our coefficients for burn rate, C and N. We check them up online or whatever. We choose our propellant to be just standard black powder, so we know the density of it. And we're making our motor in a half-inch tube. And we know that specific impulse is 50 seconds. May seem a bit low, but that's what it is for your first rocket motor. Don't expect anything higher than 50 seconds. Okay, so here are equations that I mentioned previously. So we just plug in the numbers. So our burn rate is almost 3 inches per second. Our mass flow rate is 0.04 pounds per second. And our thrust is 2 pounds of force. Now, if you multiply it by burn time, remember, if you multiply thrust by the burn time, you get total impulse. So we got 6 Newton seconds. That gives us a C-class motor. So, the motor is small, it's like that. So that should be C class. Okay, there are other important parameters. Just before you guys disconnect, don't freak out about this. Very briefly, specific heat ratio. You probably encountered this before in your fluid dynamics, thermodynamics classes. This is Cp divided by Cv. Characteristic velocity. This is a parameter that basically tells you how much you can get out of your motor, ignoring the nozzle, right? So in the first portion, it basically tells you what's happening in the chamber, right? And here's our equation, and you can see that it depends pretty much only on propellant formulation. It's going to affect your R and gamma, and it also depends on temperature. It doesn't depend on geometry, on nothing else, just that. There's also thrust coefficient, which tells you about the efficiency of rocket motor in the second portion of rocket motor. It focuses specifically on nozzles. And this is much more complicated expression, and it's different depending on whether you have cone or you have like completely no nozzle. And once you have your C star and you've got your CF, C star times CF is basically your exhaust velocity. So then you multiply by mass flow rate, you got thrust, you got everything you want. Okay, software. If you guys go to our SEDS drive, let's see. Here's our SEDS drive. We go to folder 2021. We go to folder other, solid motor class. There are a bunch of pictures. I'll discuss it later. And here you can find folder with a bunch of useful software. The software that we are interested in is CHEM and FPRED. Download these, download software installation, go for installation, and install it on your computer. And this software is very straightforward to use. I'll show you in a second. Okay, so CHEM is for propellant formulation, and FPRED, which stands for thrust prediction. I don't know why F. It's for motor simulation. Okay, so let's go to our CHEM software. Okay, nice. So it's very simple. Here you put some name, anything, whatever you like. I'm gonna go with black powder since we are making black powder motor. You check up ID numbers of your whatever you are using. So we're searching for potassium nitrate, and this is 800 something potassium nitrate. There we go, 834. So you put your ID in here, 834, and percentage 75. And you do that also for your charcoal. In that case, it's called something different. It's called, I don't remember. Let's see. Okay, carbon. Oh, I'm going too far. What's going on? Okay. Let's see. Let's see. Carbon amorphous. Okay. 248. That's what we want. 248. Our weight percentage in that case is 15. The final thing is sulfur. Let's go. Come on. Stop it. Okay. Sulfur 911. It's great. 11. 10%. Chamber pressure. What chamber pressure are we running with? Let's go to our previous example, 40 psi. Okay, exit pressure is just ambient pressure. Leave it as this. Number of ingredients free. Okay, hit calculate. Let's give it some time. And in the moment, we're going to use our FPRED software. Okay, so we've got our calculations. So we've got our density. We can copy that into our FPRED software. Where is density? There, we got it. Okay. I'm gonna name it black powder as well. C star. There it is. It's our characteristic balancing. Copy, paste. Okay. What else? What else? What else? Gamma. I'll probably use that gamma is 1.4. Well, that's the case for air in normal temperature. But at elevated temperatures, you know, at a couple thousand degrees Fahrenheit or Celsius, gamma is slightly lower, about 1.3, 1.2. These are the typical values you can expect. And our burn rate coefficient, C, is 1.21. For N, our burn rate exponent is 0.24. Okay, so let's say our propellant 0.5 inches in diameter, and let's say 2 inches long, and it's going to be end burner. Other parameters are not used in calculations, so just so that they don't confuse you guys, I'm going to set it to 0. Doesn't matter. I could leave them as they are. It just wouldn't be used at all. Okay. Should have brought my mouse with myself. Okay. And a couple things here. Okay, let's make our throat quarter inch. Why not? And we've got no nozzle, so it's going to be the same. Exit cone angle, I'm going to talk about this in a moment. Let's assume 0 for now. And that's it. Hit calculate. Okay, now we got it. So our pressure, the actual pressure that we get, if you look into the graph, it's constant. Yeah, you can see, actually here we've got exact value, 47 psi. So pretty tricky because you need to make an assumption for pressure first to calculate your burn rate and stuff. And then at the end, you get a new pressure. So if you want to be more accurate, you should use your new value, 47, plug it in here and start your analysis from scratch and do it until you are satisfied, until you've got like no more differences between this number and the previous number. So what's the thrust? The thrust, well, it's a bit more than 2 pounds. If you look into our calculations, it's a pretty satisfying number. It's very close. We got 2 pounds from our hand calculations. Then the burn times is a bit shorter than what we assumed. So that's what it is. Feel free to play with it, guys. I'm sure you'll have fun. All right. All right. One thing to mention, I forgot. Here, the density that you have in here, this is the highest possible density. If you really pack it, if you really squeeze it under enormous pressure, this is the density that you would get. In fact, when you prepare your own propellant, it's certainly going to have some voids in it. so the density is going to be lower. So let's maybe multiply it by 0.9. We got, okay, this number. Let's put it back in FPRED. Let's hit calculate again. Okay, so now you can see that our thrust dropped a bit due to worse packaging, due to worse mixing. That's why mixing is so important. You can see that slightly worse density changed our thrust a lot. We lost a lot of thrust because of that. So you need to be, whenever you mix your propellant, you need to be very, very careful, very cautious. Make sure that it's nicely mixed. And the thinner particles you have, the better it is, the better burn rates and everything. Okay, let's talk about efficiencies. Well, the mathematical model I'm putting here assumes that everything reacts at once, okay? But if you, I don't know, use microscope, you can see that there are some particles like these highlighted here of metal that are not in contact with oxidizer. That means that in reality, they're not gonna burn instantaneously. They need to wait pretty much for diffusion. They need some extra time to react, right? That's why our efficiency is not 100%, it's lower, it's 75%. That's why in FPRED we use 75%. This number, this assumption is pretty good for composite propellants, but I'm afraid that for pressed powders, for a black powder, it may be lower. It might be 50%. Let's see what we get with 50%. Our thrust pretty much halved. It went down significantly. So if we could achieve better mixing, we would achieve much better results. Next thing, divergence loss. So when you're using a standard cone nozzle with recommended 15 degrees angle, you can see that your exhaust doesn't go exactly the direction you want. It doesn't go in line with motor. It's slightly angled. That angle is alpha. And because of that, not the thrust is not directed exactly in the line of motor. Some of the thrust goes sideways, right? So you need to account for that. And it doesn't make a lot of difference. It's with 15 degrees alpha, your divergence loss is 2%. So you don't really need to worry about it. Mixing is way greater concern. But here you can see if you put 15 degrees in here and you hit calculate, look at the thrust, for example, you can see that it dropped by approximately 2%. Okay, another thing, throat or general nozzle erosion. This is very common with solids. Here we fired a motor that was initially straight, it had no nozzle, but the propellant, due to the pressure it had, it forced its way out. It tried to spread like sideways in lateral direction, and it pretty much burned the nozzle. That's called nozzle erosion. We used graphite for throat insert. You can see here that this thing is graphite, and it didn't erode that much, which is good. But it's interesting that the motor just by itself created a very interesting nozzle shape, which is not far off from optimal nozzle shape. That's why you don't worry about nozzles too much with solids, because you've got that erosion. You just cannot stop it. And the software can account for that. You can turn erosive burn on, but I'm pretty sure you need to assume, okay, radial throat erosion, mils per second. Let's go for 1 and see what happens. Okay, then we've got problems. Okay, let's ignore it for now. Okay, that's what we've done. Now, what if we want to go to something more advanced? What if we don't want end burning gray? What if instead we drill a hole in our propellant, just as in the second picture, and we ignite the entire surface within that hole? Then your frost curve is not straight. It's not like in case of end burning grain that you always have the constant burning area. No, it varies. In case of a simple, circular hole, just as in case of in the first picture, with constant burn rate, you can see that like the depth per second always constant, right? So if you go deeper and deeper and deeper, you can see tiny arrows in here. The radius increases, and each of these slices is bigger, right? It has greater area, it has greater mass. What it means is that with time, the mass flow rate increases, and therefore thrust increases. And this is known as progressive thrust curve. So that means that with geometry of your grain, geometry of that hole, you can control burn rate. You can control the entire thrust curve. So imagine if we had a circular hole and we had like second circular grain, we could theoretically achieve neutral thrust because these rings would increase in size and these would decrease. So more or less you would end up with zero. You would end up with neutral thrust curve. Now you can have a look at these other shapes, very interesting, very interesting curves. But this is just theoretical. In reality, it wouldn't work like that. Well, let's focus maybe on the last one. If you have like rough edges in your grain, there's a big risk that your grain would just split. You would have cracks, you would have explosion. You definitely don't want that. So all of these grain shapes that you see in here are useless. Even the second one. Guess what's going to happen if you fire the second one? That middle block essentially is going to plug your throat and you have explosion again. So only the first one makes sense. So is there any other way to control thrust curve? Well, yes. What if you try to combine end burning with a circular hole, right? So we would combine like neutral curve with progressive curve. So let's say your motor consists of several so-called cartridges. And each of these cartridges burns at the ends, both ends at the same time, and also on the interior. And depending on the shape of that cylinder, if it's longer, then you would have like more of that progressive effect, right? This effect would dominate. And on the other hand, if you have more of cartridges that are very short, then end burning effect would dominate. So this is the general rule. Less cartridges, yes, with less cartridges, but the longer ones, you achieve progressive thrust. With more cartridges, but shorter ones, you achieve neutral or even regressive thrust. Okay. Some time ago, I had the pleasure to attend a class. It was like a training where I got to build a rocket motor under supervision of retired NASA engineer. It was a great experience. I really recommend that you try it, guys, too. And I documented the entire process of how I built the motor. I've got a bunch of notes, and pretty much everything that is in that presentation is based on that course, on those 4 days. So I'm going to show you what we built. It was a simple PVC motor that looked like this. So here in the middle, that entire thing is the uh, combustion chamber. This is just one cartridge. And here you've got your throat. Don't worry about nozzle because of erosive burn. But we actually built something bigger. You'll see in a moment. So let's start. We start with a nozzle because they take a lot of time to cure. You can buy just simple, PVC components of McMaster. I don't know what this component exactly was. It was some kind of an adapter. Um, so the first thing you do is you just tape the bottom, and we're gonna pour some water putty in it. Some kind of cement that settles in. It works very well for nozzles. It's very strong.
Is it the same one we're using?
So you just tape it. That's it. Okay, we're gonna use some PVC glue. Make sure you get some PVC glue. It consists of two parts. The first thing is primer. It kind of like dissolves the PVC, makes it like very sticky, and then you've got your actual cement. Okay, so as I mentioned, you pour the water putty over. Here is your water putty. It's very common in amateur rockets, but it fully cures in 2 weeks. It needs a lot of time. So if you have some kind of oven, you can speed up that process, or at least if you could put that on your heater or whatever. It's really strong. It's stronger than PVC tubes themselves. 1000 psi is a lot of strength. One more thing, on top you need to put a graphite insert, just a tiny, square, half by half an inch. This is the graphite insert I showed you in the previous picture. This is going to be our throat. It's going to protect throat from erosive burn. Make sure you cover the edges of that square with putty so it doesn't come out, and it stays in place. And once it's fully settled, drill the nozzle out of desired diameter, whatever you designed it for. Okay. Then the next step is cartridges with propellant. You cut your PVC tubes to desired length, and you carefully tape the bottom. And you need some dowels. They're gonna just uh, once you take them out, you keep them in the middle, right? So your excuse me, so your propellant grain is has a circular hole in it. Yeah. So make sure that the diameter of those dowels is at least double diameter of throat. Otherwise, you risk the throat, being blocked by propellant. Cover them with baking powder just so that you can easily take them out afterwards, after your propellant has settled down. Okay, this is the tricky part, preparing propellant. I'm not gonna tell you more about this. It really depends on formulation, so I cannot tell you what you need to do, right? There's just general rule that liquids go first. So typically your binder, if you use epoxy or HTPP, this thing goes first, and then you pour whatever powders you have. If you decide to use something reactive like magnesium powder, this is difficult part, this dangerous part, because magnesium powder is very reactive. All of the aluminum, sorry, all of the magnesium, then you are safe. it's not gonna burn, right? But whenever you prepare your propellant, make sure you cover your face and take all of the safety precautions. Keep yourself safe. Here's an example epoxy that you could use as binder. So let's say you've got your propellant ready. You need to act fast before it starts to cure. This one took theoretically 30 minutes to cure, but actually after 15 minutes it was really hard to work with. So you need to be pretty quick with it. You fill out your cartridges. Yeah, make sure your dowels are higher than your cartridges so that you can take them out. Okay, that's what it looks like once it settles. It doesn't take much time. It of course depends on your formulation. You take your dowels out. Inside you may have some irregularities, but it's not too bad. Just look for some big voids. If you've got some really massive voids, that's bad. You definitely don't want this. You trim all of the excess out. Don't throw that excess away. You could always use it for other experiments. You could even make igniters out of it. Certainly going to be useful. And you even cut out more. You need to taper that. Why? Well, maybe you have seen in the previous picture. Let's go back there. Why is it tapered? Well, you need to have enough space for air to get there. If you want to all of the ends to ignite at once. That's why they should be tapered.
Wash my hands.
Let's see. Actually, that's too much taper. I made 2 deep cuts. You don't need to go that deep. Okay, and then you stack your cartridges on top of another, and you apply insulation. These are the connections are the weak spots, and actually my rocket failed because of that. So feel free to experiment. I think we used some kind of something similar to rubber. I don't remember what that was, but unfortunately, within 4 seconds of burn time, it burned through. Make sure you cover it with electric tape. Make sure that it's fully sealed. Then let's prepare casing. You can just buy a cap, PVC cap from Master. We drilled a hole in it for pressure measurements. If you're not planning to measure pressure, you can just ignore that. Just use solid cap. That's what we did. This is an insert for the pressure transducer. Would be useful for our clap too. Yeah, and this is the exact installation that we used also for the connections. We use that for the cap where that insert is. Again, if you don't measure your pressure, you don't need to worry that much about that insulation because you don't have that weak spot. And finally, pretty much just need to glue everything with PVC glue and assemble it. So here you've got your top completed. Now the entire rocket motor is completed. As you can see, it's pretty big. That was J class. So this is level 2 high power rocket motor. It's pretty powerful, I must admit. Okay, the final thing to do is install your igniter. Just don't do it like I did in the picture. Do it at the very last moment once your rocket is on a test stand, once it's ready to be fired. When you do your test, make sure that your motor is restricted in all of the directions, even in backward direction. Due to instability, motors occasionally can go backwards. It does happen sometimes. For our club, for SEDS, it would be nice if we acquired some data. The most important parameter that we should know is pressure. This thing is not expensive. It's, you could buy some data acquisition unit for 59 bucks, and we could certainly measure pressure with it, which is the exact same way as you can see here in the pictures. And then the second thing would be load cell. So when you do the load cell, design it so that the motor is horizontal, because when it's vertical, you also need to account for mass of the rocket, right? Because there's weight on the load cell, and the mass changes, right, as you burn motor. So it's difficult to model. I would rather much more recommend having motor fire in horizontal direction, so that we don't need to focus about the mass on the mass. Okay, guys. So just to conclude, safety again. If you do it on your own, make sure you have permit, use common sense, know everything about your mixture and ingredients, read the safety sheets, start with motors, and as you get experience, slowly scale up. Keep your ingredients away from your test area, keep your test area clean, keep your fire extinguisher ready, protect your face, ignite from distance, and always assume that your rocket motor will explode. There are some resources for you guys. For propellant formulations, you can start with pyrodata. It's a very simple website to use. And if you want to increase your knowledge in general on solid propellants, I definitely recommend that website here. Thanks to John Wickman. This is the retired NASA engineer that I mentioned. He runs 4-day courses and shows you how to build your own solid amateur motor. I really recommend this. That was an amazing experience. He also provided that software that I use. The course is just 250 bucks. Honestly, I would assume that this money only covers the materials for that motor. The experience that you get is priceless. I really recommend this once again. Thank you, guys. I'm going to show you finally how this static fire looked like. That was fun. All right, all right. Okay, let's stop recording.